Yeah, so hello everyone, I'm Chuteng Zhou. I'm a fourth-year PhD student working in Plasma Science and Fusion Center. Today I'm going to bring you something which may have less nuclear flavor to it, and it shows you the diversity of research that we do in this department. So today I'm going to talk about understanding plasma phase-space holes using hole tracking particle in cell simulation. And so first I'm going to start by introducing the physical system that I work with. And so on the left, I'm showing you a box of particles representing a fluid that many of you in the department are very familiar with and work with in your daily research. And the fluid is normally characterized by high density, low temperature, and is dominated by binary collisions. And on the right, I'm showing you a box of particles representing a collisionless plasma, and that's the physical system that I work with, which might be less common, and it's characterized by low density, high temperature, and it's dominated by long-range electromagnetic interactions. Because in a plasma, all the particles have charge, and they feel this long-range electromagnetic field. So we say a plasma is collisionless when the mean free path between collision is longer than the system size that we care. For example, a perfect example of a collisionless plasma would be the Earth's magnetosphere. And there, the mean free path between collision for both proton and electron is on the order of 10,000 kilometers, which is comparable to the diameter of the Earth. So the system is effectively collisionless. And a collisionless plasma has many fascinating physical properties. And the main phenomenon that I'm interested in this collisionless plasma system are electron holes. So many people may be more familiar with electron holes in a semiconductor physics context. And actually, when you think about electron holes in a collisionless plasma, it's somewhat analogous in the sense that it's a localized deficit of electrons. So here in the bottom left panel, I'm showing you the electron phase space. So the x-axis is the position and the y-axis is the velocity. And I'm plotting all basically the constant energy contours, which are the electron orbits. And you notice that some of the orbits are not connected to the outside world, so that they're trapped in this phase space. And these trapped orbits are shaded. And if there's deficit of electrons on these trapped orbits, they will give rise to a positive potential, which is shown on top. And that positive potential will in turn trap them. So it's a self-consistent equilibrium in a collisionless plasma system. And the reason why we call this structure an electron hole is because when you look at the electron distribution function, which is plotted on the right, and this is a distribution function landscape, it basically tells you for a given position and a given velocity how many electrons are there in that there's a dip in the distribution phase space density of electrons at the position of the electron hole. So it's effectively a phase space hole. And how these things can, so the reason why this is relevant in a collisionless plasma, because this distribution is highly non-Maxwellian. So if you look at it, there's a dip in the middle, and in a collision null system, it will relax to a Maxwellian. But in a collisionless plasma, this structure will exist for a long time. It's a very robust structure. And electron holes can arise from phase space instabilities. So here I'm going to show you a video of of electron hole formation. So we start with so here again I'm showing you the electron phase space, and the x-axis the position, y-axis the velocity. You have two electron populations counter-streaming. They have different velocities. They're coming towards one another. And this system is unstable. It's subject to two-stream instability. As you can see, as the instability goes on, it will form these basically phase space vortices, which are electron holes, and they will coalesce to even form bigger ones. And this is the process by which these electron holes are formed in the space. So electron holes are actually observed in space. So lots of satellites are launched to measure the Earth's magnetosphere. Here I'm showing you an example of this is a magnetospheric multi-scale mission, a cluster of 4 satellites which were launched by NASA. And each of them have 6 electric field sensors, and they do in-situ measurement of the plasma environment in which they're traveling. And in the data that they send back to the Earth, of these satellites sent back to the Earth, people notice that these satellites often encounters a very spiky structure of electric field. So here I'm showing the electric field measurement in one of these satellites. And if you zoom in to look at the detail of these spiky structures that these satellites encounter, you will notice that they're almost all composed of these bipolar structures of electric field, which is a characteristic of the electron hole, because if you take the derivative of a positive potential pulse, you get a bipolar electric field. And the mystery about these electron holes is that people don't actually know how they move. People actually don't know what determines their velocity. So the measurements from space suggest that there is a wide range of velocity for these electron holes. Here I'm showing you a plot of basically the measurement. The black circle is the electron hole velocity measurement, and I would like to draw your attention to the orders of magnitude in that velocity. So it's log scale, so basically it ranges over 3 orders of magnitude, all the way from 10 kilometers per second to 1,000 kilometers per second. And people never really understood why this is the case. And so the fundamental question is, what determines the velocity of these electron holes? And to answer this question, I think we need to have an analytic theory and also something to compare with. So what we choose here is a high-resolution first principle simulation. And today I'm going to focus on the simulation aspect of our work, because I'm not going to bore you with all the equations. And so the simulation technique that we choose for this work is called the particle-in-cell simulation. And I think the name is self-explanatory. In a particle-in-cell simulation, I'm showing a cartoon of how this code works. So basically, you have spatial grids, which forms these cells. And in the cells, you have these particles, which are plasma particles. And you do charge weighting on the grid, as this diagram shows on the right. And then you can solve for the field on this grid. And then you use the field that you solve for to solve the force that's exerted on the particles. And then you can advance the particles, so on and so forth. And this advances in time. And the challenge that's associated with doing a peak simulation for these electron holes are the following. So first, you need open boundaries to simulate these things, because you don't want the electron holes to be interacting with itself. And the holes are moving quite fast, as I say. And so it's a very localized and fast-moving object in a simulation domain. And the peak simulation is very sensitive to noise. You need a large number of particles in order to reduce the statistical noise. And so this noise is very sensitive to the particle density in that simulation. So this all imply that you need if you were to choose a static domain, you would need a big simulation domain with lots of particles, which is a high computational cost. And so the idea is why not having a simulation domain that can self-consistently follow the whole motion? And so basically, when the hole moves in the simulation domain, we'll just move the domain accordingly to track its motion, kind of like a camera tracking the object. And so in order to do this, we actually need a feedback control system. And so feedback control is a concept that we borrowed from the control theory. And you can actually do this in a simulation as well. In this diagram, inside this red box, I'm showing you the structure of a common peak code. So you have a particle mover, you have particle injection at the boundaries, and the Poisson solver to solve for the field. To do this feedback control, you need some actual blocks. And the first thing you need is a hole tracking block that tells you where the position of that feature is in the simulation domain. And then it gives you the position and the velocity of that feature. And it needs to go through a low-pass filter, because the time step we take for these simulations is very small, and the velocity is very noisy from that simulation. from that whole tracking algorithm. And then we pass this through some sort of a control mechanism. This will tell you the acceleration that's needed for the simulation domain to exactly follow the motion of the feature. And this acceleration and the velocity of the simulation domain is actually very important for the need to go back to the peak code, because the domain is no more an inertial frame of reference because it's accelerating. There's an inertial force arising from the acceleration. Also, the velocity determines the distribution that you're drawing from to inject particles. So this loop needs to be closed. Here I show you how our algorithm actually works. And on the left, again, I'm showing you the electron phase space contour. And here I'm showing you the formation process of the initial formation process of an electron hole. So you see, once it forms, it feels an acceleration actually here, in this case, which accelerates it to the right. And some people call it a self-acceleration, and it's because it's interacting with ions. And on the right, I'm showing you the red curve is the velocity of the electron hole. You can see that there's a sharp rise caused by this initial acceleration, and the blue curve is the box velocity. And the box is doing a good job to follow the velocity of the electron hole. Not only it's tracking its velocity, but also it's tracking its position to always center the feature, the electron hole in the simulation domain. And so we've done a benchmark to show that this new sort of a short domain self-hole tracking simulation gives exactly the same result as a fixed domain run. So here I'm showing you the agreement between the two runs. So we essentially can achieve the same precision, but with a domain which is much shorter. So here is a short run case is 4 times shorter and 4 times less particles. And for longer runs, we may even have a much bigger speed up, because the speed of a pico basically is, the time of a pico basically scales linearly with the number of particles in there. And the big advantage of having a whole tracking peak is that it offers a very good flexibility to explore a wide range of parameters, because you don't have to worry about losing the thing that you're trying to simulate from the simulation domain. And then here I'm showing you that we've done these runs exploring a 3D parameter space of different parameters. We've studied this initial transient acceleration very carefully, and its dependence on the initial velocity, on the mass ratio, and on the size of the electron hole. And so, and the solid lines are from our theory, and there is very good agreement. And one of the other thing you can do with a whole tracking simulation is that you can study the off equilibrium case. So here what we do is that we apply some acceleration to the ions, and we see how the electron actually reacts to it. And this actually reveals some very interesting coupling between the electron hole velocity and the ion momentum. So here the blue curve is what we call a pushing case, is that when we accelerate the ions towards the electron hole velocity, and the electron hole velocity will immediately react to it. It will also accelerate, and it's as if it's pushed in the velocity range. And in the same token, you can do pulling as well. That's when you accelerate the ions away from the electron holes. And this pushing and pulling is reversible, and it's asymmetric. And so this effect itself is very interesting, because reveals a momentum coupling, and there's no collision in this system, but because of the existence of electron holes, momentum can still be transferred from the ions to the electrons. And also this provides us with a chance of exploring electron hole of different velocities almost continuously. And so, which was especially the slow electron holes, which were difficult to access before. So we explored we discovered actually slow electron holes can experience an oscillatory velocity instability, so here I'm showing you a case of that instability. So on the left you have the potential and the ion density before the instability, and on the right you have the potential and the ion density after the instability onset. The bottom panel actually shows you the velocity of the electron hole in the ion frame. You see that if it slows down, if the velocity of the electron hole in the ion frame falls below a certain threshold, then the oscillation in the velocity actually begins to grow, and this whole system is unstable. And this, the significance of this discovery suggests that some of the slow electron holes measurements that are observed in space that I showed you before they're susceptible to this instability, so that they're candidates of driving ion heating and anomalous resistivity in space plasma. And here comes the conclusion. The simulation domain, so we use this technique of hole tracking, and the simulation domain can be greatly reduced. We studied the full dynamics of electron holes interacting with ions, and the agreement between our theory and the simulation is very good. This work is supported by NASA, and here are some of the related publications if you're interested. Thank you very much for your attention.
Thank you. Questions for
Derek.
Yeah, what's your plan for multiple holes?
Oh, for multiple holes. So, yeah, this is a very good question. So the justification for doing this solitary hole simulation is that in space, because of the main factor that will influence the hole velocity is actually the ion, is what's happening to the ions. And so normally in the context of the magnetosphere, the ion temperature is very high, so that there is strong ion Landau damping. And so the ion perturbation from one electron hole may not be able to travel to reach the other one, so that they're, in the sense that they're actually well separated, so that it can be considered as so that they can be treated separately. And also it's because by doing a single hole simulation, we're able to actually to compare it quantitatively with our theory, because I guess multiple hole theory is very hard to do, and already a single hole theory is actually quite difficult. So it offers us this quantitative comparison between the theory and the simulation. To validate our theory, actually, there's a whole theoretical aspect of this work that I'm now showing here. Yeah.
So originally, your electron hole that's already it's created. It's an instability, right?
Yeah, it's a phase-space instability.
And then you close saying that these holes are also unstable.
Yeah, they may. Yeah, they cannot travel in a steady-state fashion if their velocity is too slow.
So,
Yeah.
so what does that mean if that hole is unstable? That means that it disappears, or you have turbulence that.
Oh, it means that, yeah. So what happens is that as I show here on the right, so the whole potential will oscillate. So its velocity will oscillate, will drive these acoustic waves, and also this will lead to trapped particle detrapping, and the whole amplitude will basically decay, and it can eventually disappear. Actually, yeah. So this coherent structure will be
Your hole will disappear.
the whole will disappear, yeah. It can be destroyed by this instability, actually, yeah.
There was one more question.
Yeah.
You mentioned the generation, one of the generation mechanisms for creating these electron holes was electron-electron two-stream instability.
Yeah, yes.
Is that the driving creator of the space environment?
In space, yeah, okay. So in space, normally the instabilities are like, you can have these beams, like beam type of instability. So it can be current driven, it can be a Bunemann type of instability, which is current driven, or it can be, yeah, as long as you have like very cold beams that's somehow created by the space environment, and it will lead to the generation of these electron holes, basically, yeah. So a beam in the phase space, yeah. Did that answer your question? Yeah.
I guess the only beam is the solar wind and the sun.
Oh yeah, because.
Where's the other? I guess if you're motivating two-stream.
Yeah. So I guess the space environment is really very chaotic. There can be like these magnetic reconnection and all kinds of other particle acceleration and these violent release of energy. And these instability mechanisms, they will create these structures. Yeah.
Any more questions? Let's thank Nancy, whom I would like to thank very, very much for all her hard work and dedication to making sure we conduct this event very smoothly. So you have to listen to what she tells you.
Just two quick things. Thank you all for coming. I hope you've had a good day. I'd really appreciate it if everyone could dispose of their trash. There's bins here and in the other room. And anyone who has a poster out in the hallway, just remember please to remove it. Thanks.
Thank you again. All right, so I would like to thank also on behalf of the faculty, the really excellent speeches on the different research teams in our group, and the really high quality and exciting poster presentations. We were really, really pleased with the attendance and the work that was discussed by the poster presenters. Thank you very much for putting effort to make it a great event. And I'm not thanking you for making it difficult for us to choose the poster winner because of this. In fact, it was quite a discussion. But there were five faculty people, right? And we enjoyed many of these posters. So we could not choose one, but we chose two. All right, so I'll announce them. And so I'll announce in an arbitrary order, but equally. All right, so first one is by Yixiang Liu. So if you haven't seen her poster, that was on high sensitivity DC magnetometry. Okay, so, and the second one is Jayo Wan. Electrolysis. I had to recuse myself from the last one, so it's not my fault. You don't tear this, it's one, but it's we will print the second one. I mean, certainly, so yeah, congratulations, both of you.